Okay, guys, welcome to thermodynamics video, the first part of our notes for chapter 6. I'm gonna project them here on the screen, but wanted to talk about chemistry ornaments first. So want to talk about chemistry ornaments first. So we will have a chemistry in the back of the room when you guys return from break, provided I can get it set up or get the aides to set it up for you. But there are some things that you guys, it's the same as what you did last year, but hopefully it's not something that you're buying. It is something that you are recycling or whatever. And I'm sorry about didn't edit the PowerPoint or the PDF, but it's going to be due on Monday, December 6th. So you'll have a week after break, but if you want to work on them over break, that'd be great. Do something really creative and something cool and fun. I would show you a bunch of them that I've had in the past, but you guys saw those last year. So chemistry ornaments that you can make up to 2, and they're 10 points each unless you do something really crazy good, but you'll just get mold bucks for your stuff and, you know, kind of normal. Okay. So moving on, we're only doing chapter 6 this year. In the past, we've done chapter 6 and 17. We didn't last year, we did 6 only. But in the past, we've done all of thermodynamics in one section, but we're actually going to move the part of thermodynamics that goes along with electrochemistry into the spring. So our unit will be a little bit shorter. It'll be a little longer than last year. It's almost a full week longer than last year, which I think is a good thing. So we'll have a little bit more time with thermodynamics as we did with gas laws. So I think that should make a little bit of a difference, hopefully a big difference. Anyway, so we're going to talk first about nature of energy and just a couple of calculations. Today's pretty short. In thermodynamics, we're going to study energy in terms of chemical potential energy. So that energy that we can change from chemistry to energy that we can actually do for or use for useful work. We will focus specifically on the thermo, but it's all going to be about heat or heat transfer or energy transfer, if you like. So the relationship between energy and work, energy is the capacity to actually do work, and work is actually that movement across a distance or that force that's causing something to move over a distance. Work is actually calculated as force times distance, and we'll do a lot more of that, or you'll do a lot more of that when you take physics than you are in chemistry. But in chemistry, we're going to talk about the energy that we can actually calculate from the reaction that's taking place. So the bonds broken minus the bonds formed that we actually have from calculations. We'll do more of that, products minus reactants, of course, Hess's law and others, but not today. So the first law of thermodynamics states that it's also known as the law of conservation of energy, which basically says that energy can't be created or destroyed, but it can be converted from one form to another. So the total amount of energy in the universe stays the same. And so you can convert energy by, storing it, say, in a battery. That would be storing physical energy or some sort of energy, mechanical energy, into chemical energy. And then it could be retrieved from that chemical energy of the battery to do some useful work, turn a motor, turn on a light, or whatever. So that's the chemistry that you're most familiar with. But others are just producing heat. A lot of the stuff that we're going to do is not necessarily related to energy that you can see, but it's energy nonetheless. So energy can be classified in a couple of different ways, and you're familiar with this probably already, but you have both potential and kinetic energy. So kinetic energy can be calculated as 1/2 mv squared. If I'm not mistaken, I think that formula is on your formula chart. We're not going to use Ke equals 1/2 mv squared that often, but if you were to use it, velocity would be in meters per second. The mass needs to be in kilograms and not grams. And what it'll give you is a joule. A joule is a kilogram meter squared per second squared. And so joule is actually our base unit for energy. Although most of our stuff is calculated in this unit in kilojoules, still the joule is the base unit for energy. So that's a kinetic energy calculation. Potential energy calculations, it's not written on here, but potential energy is actually calculated as mgh. This is really not a formula we need in chemistry necessarily. We could calculate the amount of energy stored in chemical bonds, but that wouldn't really be mgh. Mgh is referring to the mass of an object times the potential energy, or the universal gravitational constant, in this case, just 9.8 meters per second squared. And then whatever that height is in meters from where it would fall to, so to speak. So we're not going to calculate potential energy this way. So this is really not useful for us. But kinetic energy is, and we will. But kinetic energy is the energy due to motion. Potential energy is the stored energy in that. So the energy stored in chemical bonds would be a good way of thinking of potential energy for us. So what heat is heat is a transfer of energy from one thing to another. If you take your hand right now and you put it on the leg of the chair, which is metal, I'm pretty sure I'm not in my classroom right now, but put it on the metal chair, it feels cold. Now, your body obviously is at a higher temperature than that, but it also has to do with the specific heat of an object, and things are going to move from one specific heat to another. They're also going to move from things that are hotter to things that are colder. And so what you feel when you touch that leg of the chair is that it feels colder. That's because you're losing energy. So there's a transfer of energy from you to the chair leg or to whatever. Heat always goes from the warmer object to the colder object, always. So in chemistry, there's kind of a different way of thinking about energy transfers and reactions. So it's this idea of system versus surroundings. So in the lab that we just did, you guys used a thermometer, a temperature probe actually, to calculate what was happening. Well, if the temperature probe goes down in energy, then your temperature probe gives you like 20 degrees at the beginning and then say, I don't know, 15 degrees afterwards. It actually lost energy to the surroundings. So relative to the temperature probe, it actually gave off energy, right? It lost energy. But what happened to the system, the thing you were measuring, it was actually inside the water, it actually gained energy from the system, from the surroundings. When you're using a thermometer or a temperature probe, you're actually measuring the surroundings of the reaction. In the case of our lab, you put a salt, some chemical compound. They were all salts. Put salts in water, and you measured, or you will measure, the heat of solution for that. How much energy was either absorbed or released by it dissolving in the water. And so usually those things, well, it depends. They can actually give off energy or they can absorb energy. If your temperature went down, it meant it was an endothermic reaction because it required energy from the surroundings to break apart that system or that salt. And so if you saw it go up, then actually the water, it released energy. It was more stable out, in the solution than it was together. So that's interesting. So when we talk about chemical reactions, we're always talking about the system for us. Most of the time, we have to actually measure the surroundings to find out what the system is doing. Hope that didn't confuse you too much, but that's kind of what we do as chemists. Now, engineers do this a little differently. They kind of look at the surroundings rather than the system because they're concerned more about your safety and stuff. But anyway, so temperature. So temperature is a measurement of the average kinetic energy of a system. We do it in degrees Celsius or kelvins. Really only going to use kelvins in terms of gas laws. And when we do all of this stuff here, we're not really using gas laws. You can use Kelvin, it's fine. But we're going to be taking differences of temperatures. And so it really doesn't matter what you do. And in terms of not having negatives, we are going to get negatives even if we subtract kelvins. And the negatives there actually tell you the direction of the energy flow or the energy change. So temperature defined here is a property that reflects a random motion of the particles, but really it's just an average kinetic energy of that substance. Exothermic reactions are going to be ones in which the system releases energy to the surroundings. So energy flows out of the system. And that potential energy that was stored in those chemical bonds is actually given off as heat. So it's changed to thermal. And the products are actually going to have a lower potential energy in the reactant. So you had to draw this in your lab, I know, but let's use a highlighter. Look at that. So over here on the left, up at the top, I'm kind of drawing on here, even though it's really not very dark. But over here and over here, we're looking. So this over here are our reactants, and this over here are our products. And so what you're doing is you're losing energy when it becomes products. So it's giving energy off. That would actually be hotter. Your temperature probe would actually go up if they lost energy. So that would be an exothermic reaction. An endothermic reaction, on the other hand, will actually finish higher than it started. So what happens there is that the potential energy is on the left-hand side over here, but it's not a measurement of degrees Celsius or anything. It's a measurement of the kilojoules. So the products have a higher energy than the reactants. And so the energy is being stored. So this would actually make the temperature probe go down, because the temperature probe is even giving energy to that system as well. So in this case, the reaction absorbs heat. So you look over there on the left, there's a cold pack there. Over here, there's a cold pack. Cold packs are usually made of ammonium nitrate, but they can be made of other substances, calcium ammonium nitrate and others. But if you shake a cold pack or you break it, what you do is you pop water on the inside, and then the water goes into the system, and then that system actually gains the energy from the water. And then if you put it on your arm, it'll gain energy away from you, and it feels cold to the touch. And so that's an endothermic reaction. So the energy of the products are actually going to have more energy than the reactants. So they have to pull energy in from the system. So these will have positive delta H values, which we'll talk about later. If I went back up to the top, the delta H over here is actually negative, because you do what you finish with minus what you started. Final minus initial, products minus reactants. If you subtract those two values, you get negative for exothermic. You get positive for endothermic. So energy is calculated in a lot of different ways. But when you calculate the internal energy of system, it's the sum of all the energies of that system. So all the kinetic and potential energies both. The thermodynamic quantities are going to have numbers and signs. So they're going to have 300 kilojoules, but it might say positive 300 kilojoules or negative 300 kilojoules. That positive or negative is telling you the direction of the energy transfer. So if it's negative, it means it's giving it off to the surroundings. If it's positive, it means that it's gaining energy. And so the system energy is increasing with positive, it's decreasing with negative. This is very much the same with our delta H values that we'll be calculating. So calculating the energy in a system, and I think this is an example in your notes and just popped up, sorry about that. But calculating the total energy of the system, you would actually calculate the heat involved, which is your Q value, and then the work, which they would tell you what it is. And there's a couple different ways to calculate work with us. It's force times distance, yes, but we'll do it in terms of energy transfer or change in pressure of gases. But anyway, if they give you the Q value, the heat, and they give you the work that was done on the system, in this case, a positive amount of work, you actually just add the two together. So you would add the negative 50 and the 35 kilojoules, and you would get negative 15 kilojoules. Pretty easy to calculate. It's extremely easy, actually. But in terms of work on gases, this is a way to calculate the amount of work, which is the force times that distance. We do it as the pressure times whatever that change in volume. So that change in volume is the distance, kind of going back to the force times distance. If you look at these two, if you increase the pressure on the system, you'll actually change that volume. So you take your pressure value and you multiply it times that change in volume, and you'll find out what work was done on that gaseous system. We'll only use this for gases, though, and we're not going to do it very often. The units for work in this case are liter atmospheres, which is the same thing as a joule. Or same thing, sorry, as a Pascal, not a joule, same thing as a Pascal. And then you can convert pascals to joules if you wanted to. There's a little bit of that in the homework. That transferring kilopascals to joules and pascals to joules is not something that we're going to test you over. You wouldn't be tested on that in freshman year in college either. So an example here, calculate the work if the volume of a gas is increased from 15 milliliters to 2 liters at a constant pressure of 1.5 atmospheres. So we've got some issues here with, we've got a V1 and we've got a V2, right? So that's our change in pressure. And then we've all change in volume, excuse me. And then we've also got our pressure at 1.5 atmospheres. Your pressure needs to be in atmospheres. Your volume really needs to be in liters. So I've got my final volume being 2 liters. I need to change my 15 milliliters to liters. So there you go. And then you just do the calculation here where work is going to equal negative P delta V. So if we plug those numbers in, your change in volume is, well, I don't know, it's final minus initial, so 2 minus the 0.015, you get 1.985. Multiply that times your 1.5, it's negative P delta V. So you get negative 3.0 pascals or negative 3.0 liter atmospheres. We'll use liter atmosphere. Pascal is what they'll use in physics for this, but it's fine the way it is. So looking at this right here, so one version of first law of thermodynamics is expressed like we said, the amount of heat plus the amount of work, which gives you kind of a sign convention for this relationship. So we're going to look at this here. So it says, which of these, which gives the sign convention for this relationship that's usually used in chemistry? What are we doing here? So, oh, okay, I get it. So heat, Q added to the system. So if you add energy to the system, that's going to be a positive value. If you add energy to the surroundings, that means give off energy, that would be a negative value. So we need something with positive and then negative, and I already see it. It's going to be either D or E. And then if work is done on the system, that's a positive value. And if work is done on the surroundings, that's a negative value. So our answer here should actually be D. If energy is done on the system, it's gaining energy. If Q is added, energy is added to the system, that is also positive. Now, our perspective is we always look at the system in chem, but whatever, that would be the change in energy. So if your change in energy is actually positive, it means it's endothermic, same as what we talked about earlier. Negative, it would be exothermic. Okay, so what we're going to do with yesterday's lab, you guys are going to have time, like after I finish talking right now, to work on your lab with your partner if you want. You can talk to other groups. We're going to actually get together collectively when we come back from break and share our data. I'm going to give you a little bit of time in class to kind of work on it, and I'll help you kind of figure out some of the calculations. But you should come to class Monday when we come back from break, knowing what your heat of solution is. Now, if you don't know what I'm talking about now, finish reading the instructions for day one. It has you do a bunch of calculations to solve for delta H for your particular solid. You also are going to have to figure out what your QCal is. Now, in first period, one person already came up and asked me about it, and she did it correctly. But you should get a value for your QCal, your calorimeter, or your CCal, sorry, your calorimeter constant, somewhere around 40 or so. It should be like, I think is it joules per gram? I think it's joules per gram. You need something around 40 to maybe 30 to 80, somewhere in there. If you've got something like 250, you did something wrong. If you've got something as low as like 1.5, that's not good either. So what it is, it's a measurement of how accurate your coffee cup was as an insulatory device. So how good it kept the heat in. You didn't have a lid, I realize. So that might be something in your, your conclusion in the lab that you could say, wow, well, sure, it would have been better if we'd had a lid. But lids don't really make that much difference. They make some difference. They don't make that much difference. Could have used some other type of cup, I suppose. Yeti cup, maybe? I don't know. But you should get a value that's low, but not too low. Something 40 to 80 would be really good. But anyway, so we'll talk about this. It says here, discuss your procedures for Tuesday. We actually have the second day of this lab when we come back on Tuesday. We'll talk a little bit about it on Monday when we get back, but we can share some of that data on Tuesday. Tuesday, I'm going to give you guys a cold pack. We're going to cut it open together and look at it and figure out how much energy a cold pack could actually absorb, a whole cold pack rather than just one small amount. But you're going to need to just use a small amount of it to figure it out. So see if you can kind of come up with how you're going to do that, but we'll discuss it on Monday when we return. And this is what we'll fill out. So we'll have lab data there were 2 samples of each in each class. We'll look at it and we'll fill this in for whatever those values were. And then we'll take an average of the 2. What we'll probably do is if some of them are really bad, we'll throw them out. Sorry, guys. I'll tell you, your data is bad. We're throwing it out. We use the other data that's better. And we'll compare it to the data because I went through and did all these as well. We did not do lithium chloride, but we'll recreate this chart and do this when we get back on Monday. I think that's all I want to talk about. Yeah. Okay, so that's it. Short lesson, I know, but you guys have a great break while I'm gone. All you've got really to work on is the lab. And that's about it. If you need something, shoot me a Schoology message and have a great break.